example 8.7, we've got a uniform ladder 10 meters long, weighing 50 newtons, resting against a frictionless wall, and if the ladder is just on the verge of slipping when it makes a 50-degree angle with the horizontal, find the coefficient of static friction between the ladder and the ground. So the forces, I'm going to go ahead and name them, give their distance from the center, their angle, theta RF. Oh, I forgot F. Let's make that column F, and the next column theta RF. And it helps if I use a pencil. Okay, and there are basically three things that are acting on this ladder. The ladder's weight itself is acting with a force of 50 newtons. And since it's a 10-meter ladder, that weight is being applied at its center of gravity. It's a uniform ladder, so that is going to be 5 meters. And the angle, let's look at what the angle is. Going to draw the R is the length of the distance from our fulcrum point. Okay, actually we should choose a fulcrum point before we do that. I did say this is 5 because it's the center, but the reason I'm choosing this as a fulcrum point because we have the force of the floor over here. We've got the force of the wall over here. We've also got a force of friction, a normal force of the floor and the force of the friction. Both of those together add up to be the force of the wall, or force of the floor. But anyway, the weight at r equals 0, at r equals 5. But this one, okay, this force looks more complicated than this force, right? So we're going to treat this as, put this at 0 so we can calculate it separately. So the floor and the wall has a r equals 0, the wall has a r equals 10. We don't know what the force of the wall is. Force of the wall, we do know that its angle is that way. And if this is 50 degrees, then this angle is 180 minus 50. R, I drew that R there earlier. Okay. The angle from the R to the F is counterclockwise, so it is positive 180 minus 50, which is 130 degrees. Okay, and then from the floor, we actually don't know the angle yet, or, well, it's just not applicable. And the force is unknown still. The weight, the angle of the weight, okay, let's look at that. Weight is going this way. The R is going this way. The angle from R to the weight comes this way, and we can see that this is 50 degrees, and this is 90 degrees. So 50 plus 90 is 140, and we're going clockwise, so this is going to be negative. So now that we've got those angles, let's break this down into a torque column, a force in the x direction column and a force in the y direction column. And the weight of the thing is purely in the y direction, and it's going down, so it's be negative 50 newtons. But the torque is going to be RF sine theta. So 5 times 50 times sine of negative 140 comes out to be negative 160.7. So this is the torque of the weight equals negative 160.7. Now, we know that the torque of the floor is 0, so the torque of the wall is radius 10 times the force of the wall times, did I do the angle on that? I didn't do the angle on that. Oh yeah, times sine of 130. It's right there. Equals, adding those together, we see that the torque of the weight plus the torque of the wall is going to be 0. So 7.66 F sub W minus 160.7 equals 0. And we will find that when we solve that, we get a force to the wall of 20.97. So everything works out. The force of the wall is 20.97. The torques add up to 0. And this is going to have to be broken apart into an x component and a y component, though. Actually, let's make a little distinction here. The theta of the xy coordinate system. The weight of the object is going purely straight down, and so if we were using x, theta x to our vector, theta, let's call it theta xf. Theta xf. Yeah, so we're going from the x coordinate to the force direction. Theta xf would be 90 degrees for the weight. For the floor, we actually don't know, because part of the force from the floor is the normal force and part is from the friction. But we were told there was no friction in the wall, so it's going to be purely the normal force of the wall, and theta from x to the wall is going to be, what, 180 degrees? Yeah, basically 180 degrees. So make sure that that negative sign is prominent. Okay, so the force in the y direction of the wall is 0, and the force in the x direction is 20.97 newtons. And for the weight, there's no force in the x direction. For the floor, well, that remains to be solved. We want the total force in the x direction to come out to be 0, and the total force in the y direction to come out to be 0. So in order for that to happen, this needs to be negative 20.97. and the force in the y direction needs to be positive 50 newtons. Okay, if you think about that a little bit, you'll realize that I have things pointed in the wrong direction. The wall needs to be pointed negative direction, and the floor needs to be pushing in that direction. So this 180 degrees was correct, but um, I just, for some reason, didn't grab the negative sign off of that. So the force of the floor is going to be the coefficient, or it's going to be the frictional force, mu sub s mg, of the ladder, and then it's going to be the normal force acting up. So there's two components of the floor's force. So we want to solve it by because we want the coefficient of friction of the ladder. So mu sub s times the weight of the ladder is going to be the force in the x direction. So mu sub s equals, the force in the x direction is 20.97, and the weight of the ladder is 50 newtons. So the coefficient of static friction here comes out to be 0.419, and that's rounds to 0.42 about. Okay. That's a higher coefficient of static friction than you want to count on. I think the closer you can make this angle to 90 degrees, the better off you'll be. And you'll find less and less of the ground force needs to be devoted to friction, and more of it is in proportion of it is in the normal. Oh, I was pointing without the camera on it. 3, 2, 1. So it's probably better if you don't have the angle of the ladder be 50 degrees. You probably want it more to be 80, 90, 80, 85 degrees, so that there's less of the required coefficient of friction for the floor. Remarks. Note that the torques are computed around an axis through the bottom of the ladder, so that only P and the force of gravity contributed non-zero torques. The choice of axis reduces the complexity of the torque equation, often resulting in an equation with only one unknown. Question 8.7. If a 50 Newton monkey hangs from the middle rung, would the coefficient of static friction be A doubled, B halved, or C unchanged? Alright, well, first of all, hanging a monkey off of the middle rung of the ladder has no effect on the coefficient of friction. However, I think what they mean is, what effect would it have on the minimum coefficient of static friction necessary to keep the ladder from slipping? Okay, first of all, if you put a 50 Newton monkey in the middle of the place, you change the weight at the 5 meter mark to 100 newtons. That would increase the torque to the clockwise torque to double the amount, and hence would increase the counterclockwise torque required by the wall to double the amount, which would in turn result in a horizontal force of double that amount, of double the amount, and 4. So that means that the horizontal force caused by the wall or by the floor would have to be double the amount. And finally, you'd have mu sub s mg equals twice the amount. Mu sub s mg equals twice the amount, but you've also got double the mass, so 2 f sub x. So it ends up being mu sub s would be unchanged. Exercise 8.7. If the coefficient of static friction is 0.360 and the same ladder makes a 60-degree angle with respect to the horizontal, how far along the length of the ladder can a 70-kilogram painter climb before the ladder begins to slip? So once again, I'm drawing my 60-degree angle. The ladder weighs 50 newtons and has R equals 5. The person weighs 75 kilograms. We'll go ahead and change that to a force. 75 times 9.8 is 735 newtons. Then we'll take the wall and the floor and the person. Okay, person is right here. The angle is 60 plus 90 is 150 degrees, and the same with the ladder. The wall is aimed this direction, so R to F is, this angle is 60. 180 minus 60 is 120 degrees. And the floor, for now, we'll put it at the 0 point. And the F is unknown. And the angle, I think that's also unknown. Checking my signs, the ladder, the weight of the ladder, R to F, that is a clockwise torque, so this is going to be negative 150. The person is also negative 150, and the wall has a positive 120 degrees. And the wall's R is 10 meters, and the person is, we don't know, that is what we're solving for. We'll call it, well, I don't know. We'll call it little l. Now that's, yeah, that'll work. And we'll call this F sub W. So the torque caused by the ladder is RF sine negative 150, which is negative 125 Newton meters. The torque caused by the person is 735 times negative 150 L, which is so negative 365.5 times L, and the torque caused by the wall is 10 times the sine of 120 times F sub W, which is 8.66 F sub W. Now looking at the angle between the X horizontal, the horizontal right coordinate, and the force is negative 90, and 180 for the wall. So the forces of the x direction for the ladder and the person are 0. The force in the y direction is negative 50 newtons because he's pulling down, and the person is negative 735 newtons, and the force of the wall is 0. That means that the floor's force must be 785 newtons in the y direction. And the force of the wall, and these two have to cancel out. The force of the wall in the x direction and the force of the floor in the x direction. Okay, so now we have two equations, two unknowns. The first equation is that the sum of torques, whoops, I need to put that on another row still. Total, put the 0 down here and the 0 down here and the 0 down here. The sum of the torques is equal to 0, so negative 125 minus 367.5 L plus 8.66 F sub W equals 0. And the other one is F sub W. Actually, no, that's probably enough. Well, we'll need another one that says that the force of the wall is less than mu sub s mg, and let's put a sum of masses in there. Sigma mg. So this one we'll solve for F sub W in terms of L. And the mu sub s mg is mu sub s times the sum of the weights. We'll have 50 plus 735, and our mu sub s was given as 0.35, 0.36. So this is the maximum force of the wall. So I can essentially take that force of the wall, plug it in right there, and solve for L. And the final answer I got was 6.32 meters, which is pretty close to what they have here, 6.33 meters. It would have been easier to do this problem if I'd realized this sooner. Then I could have plugged in the force of the floor right here, 282.6, because I knew the mass times gravity, and I could have plugged in 282.6 here and found out the force of the wall was 282.6. Well, okay, except for doing it wrong. This is not 282.6. This is still a question mark. But the force of the wall is 282.6, which makes the x component of this 282.6. And that would have been, that's the one thing we haven't actually calculated yet, the force of the floor. But we do know its x component and its y component.